Alright, welcome to page 3 of the notes. And here we're basically going to just show you how to do the actual computations of just the addition of vectors or the difference of vectors and multiplying by a scalar. And so basically all you do is, when we're adding vectors, they need to be of the same type of dimension. So that in this case, A is 2 dimensions and also B is 2 dimensions. And so we can add those, and all we're going to do is we'll be adding the same coordinates. So we'll be adding the first terms, which are representing the x, and then the second coordinates, which will be representing the y's. We add that together, and then we'll be getting a new vector, and that's the vector of a plus b. Same thing with subtraction. We're going to subtract, just matching, in the same coordinates, a sub 1 minus b sub 1, a sub 2 minus b sub 2. And if they're scalar multiplication, we're just going to multiply every value in that vector by whatever scalar we have, so c. All right. The length of the two-dimensional vector a, which we have as a sub 1 and a sub 2, is, so to find the length, it's going to be denoted by, it looks like absolute value signs, but that is going to be to find the actual length of a, and all it is the square root of the first term squared plus the second term squared. So the sum of the values in our vector, and take the square root of that, and that gives us the length. And again, for the three-dimensional vector, it's not much different. To find the length of the three-dimensional vector, we're just going to make sure that we add in that third term underneath our radical. All right, now here it says the length of the vector is also known as its magnitude. You should be familiar with this kind of notation back from Calculus 2, especially when you're getting into parametric equations. And one thing that you need to know about magnitude is that, we refer to it as magnitude in this class, but in other classes that deals with, 3 dimensions or 2 dimensions, and you're dealing with vectors, magnitude also is known as speed, so like also in physics class. Now, one thing here says is I prefer to use a notation of kind of like, a double lines on both sides of our vector, just to kind of differentiate that between the absolute value a. But most problems in the textbook are going to have just, the single line on both sides of your vector. And so it's up to you. You can use either notation. I myself am probably going to use the single line instead of the double line. And so now what we're going to do is we're going to just find these 4 different vectors that we have, the sum of a plus b, the sum with some scalars, 2a plus 3b. We're going to find the distance of a, or the magnitude of a, and then also the distance or magnitude of a minus b. Alright, so I'm going to zoom in a little bit just so that I can create some room, and we're going to do a plus b first. And so when we're adding a plus b, that's going to give us our first terms added together, so 4 plus 1. And then 1 minus negative 2. We do the math there, and we are going to get 4 plus 1 is 5. 1 minus negative 2 is going to, I don't know why I put minus, that should be plus. And so 1 plus negative 2 is going to give us negative 1. And of course, I'll highlight this to denote that this is the solution. Alright, now let's find the vector of 2a plus 3b. And so we're going to do 2 times 4 plus 3 times 1. And then 2 times 1 plus 3 times negative 2. 2 times 4 is 8, plus 3 is going to give us 11. Let me make sure I put the vector notation. It's going to give us 11. And then 2 times 1 is 2. 3 times negative 2 is negative 6. So 2 plus negative 6 is going to give us negative 4. And there's our vector answer for that one. Alright, next we're going to find the distance or magnitude of A. So I'm just going to take the square root and all my values for A and square those and take the sum of that. So 4 squared plus 1 squared. And delete. That's a small eraser on there. There we go. Alright, and so we have 4 squared, which is 8, 1 squared, which is 9, so we have the square root of 9, which is going to just give us, 4 squared is 16 plus 1, so we get the square root of 17. Now, the last one is we're going to find the distance or magnitude of A minus B. So the thing that I'm going to do for this one is I'm going to go ahead and find, what's the vector A minus B. And so I'm going to have A minus B inside, and I'm going to do 4 minus 1, and then 1 minus negative 2. And that's going to be the vector A minus B. So now I'm going to be finding the distance of 4 minus 1, which is 3, and 1 minus negative 2, which is going to give us just 1 plus 2, so 3. And so now I'm finding the magnitude of a vector 3 and 3. Take the square root of that. I'm going to have 3 squared plus 3 squared. That's going to give me 9 plus 9. So I have the square root of 18. And of course, I can simplify that to being 9 times 2. Square root of 9 is 3, so 3 square roots of 2. And of course, that's a solution. Right? And that's the distance. Now, again, you're seeing vectors in, everyday life here, these are not actual vectors, but it does, give us a glimpse of, it gives us, the speed of the wind, so like 40 miles per hour, and it also gives us direction. So we can just look at this one at Charlottesville. So we're just going to compare 2 of these, all right? And so let's look at Charlottesville. It says that, the wind is going south east at 23 miles an hour. And so if this was a true vector, we would denote that by, say, that vector. But, let's look at Lexington Park, and now we have the direction of that wind, but it's 48 miles per hour. And so the direction would still be the same, but to represent or to differentiate between 48 and 23, the vector would be much greater. And so that would tell us that, the wind is much greater at Lexington Park than it is in Charlottesville based off of the distance of our vector, how long it is.